car is coming around a circle like this, okay? So the forces acting on the car would be the weight, and the normal force. They're balanced because it's on level ground, it's not on a ramp or anything like that. And what force is keeping it in the circle? What is the centripetal force? In this case, it is the force of static friction, not kinetic friction, because even though it's moving, the tires are not actually moving relative to the road. The tires come down, they grip the road, then they move off the road. If you're talking about kinetic friction, then your tires are slipping. So most questions don't even mention, they won't even say the car is not slipping. But some questions go out of their way to tell you the car is not slipping. That's just their way of saying, make sure you don't put kinetic friction on there. Okay. So, as usual, we'll apply Newton's second law in the x and in the y. In the x, it's just the force of static friction, which is mu s Fn. And that's giving us our centripetal acceleration, it's causing that centripetal acceleration. And in the y, we've got Fn minus mg equals 0, which of course just means normal force equals the weight in this case. And we want to figure out, let's say the question's asking us for the speed of the car, okay, like we did in class, given a known coefficient. So we're going to take this equation, we're going to make that substitution. So mu s equals, or mu s mg, because Fn equals mg from this equation, equals mass times v squared over the radius. I substitute v squared over r for the acceleration there. Masses go away, which is good. So then our speed would just be the root of r mu g, square root of r mu g. Now the other way that this problem can become more complex would be, let's say that instead of the asking for the speed, I was asking you for, I don't know, the period or something like that. It doesn't really make sense for a car. I mean, if the car was just going around a circular track over and over, like Indy 500 or something like that, or NASCAR, then maybe that would make more sense. But it would just be a matter of doing the appropriate substitution and then just continuing the question. So we're scoring both sides and solving, and then you can solve exactly the same way. Okay? So that's sort of the general, the bones of a static friction as a centripetal force style problem. Any questions about that? Okay, and now the other type of car problem is car embanked, off ramp, or on ramp. This time we've got weight vector straight down. There's no friction vector. If there were a friction vector and you were on a bank, the friction vector would still be toward the center of the circle, but friction always has to be parallel to the surface. So it wouldn't be toward the center of the circle like this, it would be toward the center of the circle down. Then a component of friction is part of your centripetal force. That's why question 7 on the problem set is so difficult, but we're not going to worry about that for now, because we're just going to pretend there's no friction. It's a really icy day, and we're really just relying on the bank to help us around the circle. Okay, so we have to resolve some components here. So now our centripetal force is the sine component of the normal force. So sum of the forces in x equals sine component of the normal force, and this will give rise to our centripetal acceleration. And then y, we've got Fn cos theta minus mg equals 0, which leads to the relationship Fn is mg over cos theta. All right, so now let's say that in this problem, same thing, we're going to solve for the speed. So I'm going to get an equation arranged for speed. So let's make that substitution, our normal force, into our first equation. So we have mg sine theta over cos theta equals mass speed squared over r for our centripetal acceleration. Masses go away. Sine theta cos theta is tan theta, so we have g tan theta equals v squared over r. So b will be the root of rg tan theta. So given a certain banking angle and a radius, you can calculate the maximum speed that a car could do and still remain in uniform circular motion. Yeah, so there's the G tan theta. The answer to life, if you're a circle.